on, and I'm going to restart the browser. Okay, so everything is good. Just have to restore everything. There we go. Lots of tabs. Okay, so this is what I was talking about. I recorded this about 13 hours ago, which was last night, right? Last evening. And it shows you, the new trace analyzer tool, which allows you to kind of track down, what your program is doing. Okay. So what we'll do today is kind of first take a look at that tool, and then we'll go back and look at the program that I was attempting to hack, but I couldn't find the program last time. So that's what we'll do today. All right. So I got a lot of tabs to restore. So this is the tab that the recorder was recording. This is me running the Tower of Hanoi program. Remember the Tower of Hanoi program that we talked about last time? I actually finished the implementation. I was only about this far away from actually finishing the Tower of Hanoi program because I was missing one more copy and paste of the recursive call. So I finished it, and when I ran the program, this is the trace produced by LogicSIM. How many rows do you think this trace has? I mean, just give me a guesstimate. 700 and something. So it would not be very practical if you were to kind of go through this manually to try to figure out what your program is doing. Okay? So what I did was I developed a tool, or I extended the tool that we already have. So this part you should be familiar with if you have used this tool. So everything up to column L is directly coming from the trace generated by LogicSIM. But this part is new. Column M, N, O, and P are new. And they serve the purpose of summarizing what the processor is doing. Okay, so this can be very helpful when you're running a program and you have no idea why the program is not working. Obviously, it's not going to be helpful if you're one of those people who can get the program working perfectly the first time. So you can basically ignore me for the next 15 minutes if you're one of those people. But if you're one of the people like myself, making all kinds of stupid mistakes and need tools to help debug a program, you might want to actually pay attention because this tool can potentially help you figure out what your program is doing. So the first column that is very helpful is column O. What column O does is it keeps track of the program counter. Can someone remind me what the program counter does? What does it keep track of? An address in RAM, and what is significant about that address? For what purpose? The instruction, very good. Okay, so column O is telling me that I'm reading instruction from location 00, location 1, location 3, location 5, and so on. So when you look at the trace just by itself, that may not be very helpful, right? Because what is the instruction at location 0? What is at location 1, and so on? So the next thing you want to do is to look at the assembler's output. And I have to figure out which tab has the assembler's output, but it's one of these. I'll find it eventually. This one. There we go. So this is the assembler, and within the assembler there's one tab. Oh, you cannot see the tab because I put it too far down. But there's one tab here that has the name of source debug. So you might find that useful when you use it in conjunction with the trace analyzer. So when you click on source debug, it will display the source in one column, which is column A. That's the source code. That's what you type, including the comments. But it will also show you the address of the opcode in column C. So with this and the trace analyzer, you can basically cross between these two and know how your program is running. So you can track down, for instance, if your function or if your program has functions, such as this one, which has Hanoi as a function, and we know the first instruction of Hanoi is going to be at this location. at location 1D. So now, every time column O of the trace analyzer shows 1D as the address, what do you know about that? We're at the entry point. Yes? It's running Hanoi from the beginning. We just called Hanoi from somewhere, right? So why would that be significant? Why would that be useful? Sorry? You can at least track down when you're calling or when you're in Hanoi, right? Okay. So let's take a look at other columns of the trace analyzer. So the other columns of trace analyzer, column M is for writing to RAM. Whenever there's an instruction writing to a RAM location, something is going to show up on this column. And I'll show you a few examples. Right here. FF gets 02. Now, if you vaguely remember the program that we worked on Tuesday, what was the first thing that we have to do when we called Tower of Hanoi? We have to pass the parameters. And what was the last parameter? It's the number of disks, right? And we used 2 in the example program. This is the writing, this is the push of that 2 as the last parameter. Yep?
Do you need also to check if from is less than?
Nope. Nope, they do not have any specific ordering.
Okay.
Yeah, so the 0, 1, and 2 are only identifying which column we are talking about. I could use 153, 135, 16, 6, and then 12 or whatever. It doesn't really matter. They just have to be unique so that we can tell which column is the from column, which one is the to column, and which one is the via column. Yeah, so those are just ID numbers, identifiers. The next time we wrote to RAM is this location here. Location FE is getting the content or getting the value of 01 in hexadecimal. And what do you think that is? I mean, the 02 earlier was the last parameter, last argument. What do you think this one is? The second to the last argument, okay? So we keep pushing stuff like this, okay? This is going to be the second argument. This is going to be the first argument. And then we have something else to push. What is that? The return address. But how do we confirm that this is the return address? We go back to the assembler output. So when we go back to the assembler output, which is here, and what was the location again? I can't remember. 19 in hexadecimal. So you look up 19 in hexadecimal, and 19 is right here. Does that location look like a location that a subroutine would return to? Well, if it is not a location that the return is returning to, how can we possibly end up executing here? Yep.
It says LDI in register A.
Yep. Dot 6 plus.
Yeah, the point 6 plus.
Yep. Exactly. And there's no other way for us to continue execution here because this is immediately preceded by a JMPI to Hanoi. So we have an unconditional branch on row 20 to go somewhere else. So the only way that we can actually execute on this row, which is at location 19, is somewhere we branch back to this location. Is that okay? Now let's just say that you're debugging this program and you want to find out exactly when am I returning to this location. Now, getting back to the trace table here, how can you find that out? How can you find out when we return to main? Because that's in the main subroutine. Which column are you going to check when I want to find out, okay, when are we returning to main? Did we ever return to main to location 19? How can I find that out? Which column should I focus on? Yep.
You look at the execute column for 19.
We look at, exactly, we look at column O, which is execute at, and then you try to find 19 here. When you find 19 in this column, that is the exact moment that the subroutine returned back into main. Is that okay? So I'm not really sure whether you guys understand how this particular spreadsheet can really help you debug your program, but I can tell you that if I have to write a complex program, writing it in assembly language, this is far more useful than even a debugger. Why do you think this is more useful than a debugger? Exactly, because in a debugger, you have to have a suspicion of, well, I think something is going on here that is not right. And then you put a breakpoint there, and then it stops execution. Then you check a few things, then you continue execution, right? What if you say, darn it, I forgot to check blah, blah, blah. There's no way to go back in time to check blah, blah, blah. But in this case, it is logging everything that is observable from the outside. So if you forget to check something in one particular run of the analysis, guess what? You can go back and check it again. What if you say, I'm really sick and tired of having to go through this manually to find something? What can you do? Come on, this is a spreadsheet. You can write formulae in a spreadsheet to help you locate things. You can use lookup, you can use match, you can use all sorts of tools in a spreadsheet to help you locate things. So I'm giving you a basic tool on which you can extend it, right? The extension is really just the additional spreadsheet formulae. Okay? Are we okay so far with this? How many people remember how to generate something like this? Okay, the raw output from LogicSIM looks like this. But do you guys remember how to make it look like this? Does anyone need a refresher, or do you guys don't care? Refresher, okay, very good. I was hoping for don't care so I can just kind of move on and talk about something else. I think it borderline cynicism or sarcasm. It's okay. I like that. All right, so let's go ahead and go back and look at the command line that we need to get this to work. And yes, the recorder is on this time. Because I remember last time the recorder was not on, and then we just went through a whole bunch of stuff, and then we found out that, oh man, it's not working. Okay, so the first thing we need to do is to get the RAM file first. Okay, so to get the RAM file, we get back to the assembler tab, which is over here, and then we go to RAM file. Okay, right there. Okay, and then we click File, download as CSV, and we'll call it Hanoi.csv. So that part is pretty easy to do. The next thing we need to do is to run this program, but we are not going to run it the usual way. In other words, we are not running LogicSIM in a user interactive mode, and instead we try to run it in batch mode. Okay? So to run this in batch mode, okay, I'm just going to be a little bit lazy here. I'm going to use history to find out how I did it last time, because it's really long, and I don't want to have to remember how to do it. So if you look at this command here, this is how we can generate that log file. Okay, so do we have any questions here? Nope, we're good? All right. So this is the command to run LogicSIM so that it is not giving you the GUI interface. Instead, it is going to run the program until the halt pin becomes a 1, and it gives you a log in the form of a TSV or a tab-separated file. So now I just need to say repeat history entry 1815, and it's going to run it. And it said it cannot open file. Okay, which one? Oh, I gave it the wrong. It's not called return, it is Hanoi. There we go. So just a quick explanation of the command again. Java needs to be installed, so that you have to make sure that you have Java installed and it is on the system path so that you can run the program like this. Dash jar, and then you have to specify the location of the jar file for LogicSIM. Okay? So it's usually in your download unless you move it somewhere else. For those of you who are using Windows, you cannot use the exe version, so you have to download the jar version of LogicSIM to get this done. The next one is processor/processor0003.circ. That's where you put your processor circuit file. And then we have dash load. Dash load is going to put this file into RAM because that's where our program is. Okay, so all of our opcode is located in RAM, and dash load is going to load the content into RAM. Dash TTY table is what specifies the format of the output. So our output is going to be looking like a table in TSV format, tab separated format. And then this part here is capturing or redirecting the output to temp/log.tsv. Obviously, the file name, you can choose whatever you want, but you basically just press the enter key, and this time you got it done. The output, is exactly what we saw earlier in the spreadsheet. So this is basically the raw output from LogicSIM running the program. And once you import it into the trace analyzer, then it will look like this in sheet 1. And then what sheet 2 does is it will automatically process the content in sheet 1, and it will figure out when you wrote to RAM, when you read from RAM, what you execute in the program, and also which register got changed. I forgot to mention that earlier. Column P is also significant. It is also important. Why do you think column P is also important? It only tells you which register got changed. Why is that important? And which register is particularly in the stack pointer, which is register D. So if you just locate all the changes to register D, that will tell you how you are changing the stack pointer. And then when you combine that with how you're changing the content on the stack using column M, you can figure out how you are using the stack. You can reconstitute the content on stack at any particular time. It would take some work to do it, but it will give you the idea of what is going on, how you're changing the stack pointer, how you're changing and reading stack content as your program execute. Is that okay? Now, I can give you an example. This is 19 in hexadecimal. It is stored in location FB. So this means at some point I'm reading that location, right? Because it doesn't make any sense if I store something in the stack and not to refer to it later on. Does that make sense? So because this is a spreadsheet, we can use a spreadsheet function, or this is not even a spreadsheet function. We can just search for it. So we can go look. Where's search? Find and replace. There we go. So we just need to go find star FB equals, was it 19? Like that. So what this is doing is it is locating a particular cell where the value indicates we are reading from location FB, which is on the stack. That is the return address back to main. If you cannot find it, it's a problem. It means your program never returned to main. Okay, that's a problem. Now, if you can find it, you can at least find out when you got it. So once you specify the search pattern, you click find, and we have exactly one entry. Let me put this away, and it is right here. And this is really close to the end of the trace. You can see there's not really a whole lot happening after that. So this particular program did return back to main correctly, and then continue execution, which is just cleaning up the stack pointer, and then eventually get to the halt instruction. So I'm not really sure whether you guys understand how helpful this particular program or this tool can be. Are there any questions other than I really don't understand how this is helpful? In the Windows environment, the syntax of the command would be a little bit different, but it would still be the same concept. So in other words, your command is going to look kind of like this, except this is going to be C:\\, because in Windows you use backslash instead of // And if you use your thumb drive, which I highly recommend, because if you use a thumb drive instead of the school computer, then whatever you're doing is saved on the thumb drive. So it'd be like whatever drive letter, colon, backslash, and then whatever subfolder structure you want to use, blah, 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 blah. This part would be the same. This part is where you put the processor 0003.circ file. Once again, it's going to be drive letter, colon, backslash, and then the rest of the path. The rest are the same. I mean, all you're changing is how you specify a path to a file in Windows. Yep.
What I did at home is just I changed directory into the folder.
Yeah.
And ran that command from there.
It is very handy when you put all the files into the same folder. So if you put all the CIRC file, your CSV file, and the TSV file all into the same folder, then you don't have to specify these long path names. So that helps in terms of making it easier to access. Okay, so did I answer the question? Okay.
But the question was that we have a video from it. So you. Oh, this is the video. I'm sorry.
Anything else? Are there any other questions about how to use this tool? Because I made this tool, to help you guys, write the program, and also gain a better understanding of what is going on when your program is running. So I'm hoping that you will find it useful. Okay. So are there any questions about this tool, the trace analyzer? No questions. Okay. I did not have time to incorporate symbol decoding into this whole thing. So instead of showing you, like 19 or some other location, if I have enough time, I could use the symbol table from the assembler so that it can display symbolic label names instead of actual locations. But I just didn't have time, from within one day to do that part as well. Yep. Oh, these are really useful too. So columns Q, R, S, and T, they are the values of the registers prior to the change. So these columns, Q, R, S, T, would not be useful if P is empty. If column P is empty or blank, ignore that, okay? It's not useful at all. So for something like this, in column P, where it says D equals to FB, it means register D, which is our stack pointer, got updated to FB. Then the natural question is, from what, right? So now you can compare that to what it was before. It changed to FB directly from F7. So this time we know it's not incrementing. It is actually increased by a bunch at the same time because we are cleaning up after the arguments. So we are adding 4 to the stack pointer and changing it by 4 this time. So thank you. That was a good thing to mention because otherwise people would be asking, well, A is 19 now, but what was it before? Well, A was 04 and then it got changed to 19. You just have to keep in mind that we are looking at hexadecimal digits and not decimal digits. So keep that in mind when you read the trace. Any other questions? Okay. Did anyone run into any problem like when you run the program, it is not getting to the halt instruction or it is not doing what it is supposed to? Okay, this may help. Now you also may want to insert halt instructions into specific locations so that the program would actually stop, because the trace would not end until we get to the halt instruction. So if your program doesn't get to the halt instruction, then there's no way to actually capture the file because it's never done. So are we good? Yep, go ahead.
At some point when I was using the assembler, the scripting broke, and I wasn't sure how to fix it, so I had to re-download everything.
Okay.
Is there any way to look at what the script itself is?
Which script?
That generates the files.
Are you referring to this command?
What happened? No, I mean on the...
In the assembler?
Yeah, the Google spreadsheets.
Mm-hmm.
I had two lines that were just stuck being errors permanently whatever I did.
But when you refresh, when you copy the assembler again, the error went away. It still stay there?
You would go to your folder and make another copy of
Then you fixed it, right?
Yeah.
That means you might have made some accidental changes to the spreadsheet itself.
I think it forces you if you try to modify anything in the other columns.
I can take a look if you still have the one that is broken. Okay. Yeah, if it doesn't work, it's usually because, there's an accidental change to one of the formulae in the spreadsheet because, after all, if you change one little thing, the whole thing can potentially break. All right, so do we still have any additional questions about the tool or the general approach of how to get started and how to debug a program for the Fibonacci homework assignment? No questions? All right. So shall we hack the program that I found? All right. So you can access that program too. The program is actually on Canvas right now. So let's go to Canvas and take a look at that program. I put it into the same module as the rest of the stuff that we're doing recently. So if you look it up, it is right here. It's called hack1.stripped. Okay? So we're going to click on it and then download it. It's a really small file, 4.6 kilobytes. So it's a tiny little file. So we click on it, and then you can save it anywhere you want. Now, you're not going to be able to run it unless you're running Linux. So if you're using Windows, you won't be able to reproduce the steps that I'm doing here. OK, so once it's downloaded, where did I download it to? Temp? OK, I thought so. So we changed folder to temp. The first thing I need to do is to change the permission so I can actually execute a file. So I change the permission. Then I can just run the file. So when I run the file, the first thing it does is to ask me for a password. So I can give it a random password. And it tells me, read the fine Digital Millennium Copyright Act. It's an abbreviation. Read the fine Digital Millennium Copyright Act. OK, nobody's laughing. What is the Digital Millennium Copyright Act? Well, and what does it specify? How does it stop people from pirating and stealing stuff? What does it make illegal? Does it make it illegal to possess copyrighted material that you just remove the copyright? Go ahead. The act of copying is certainly illegal, but they also make the investigation of how to circumvent copyright protection illegal. So if you are a scholar, a researcher, okay, and you're just out of curiosity, you want to find out, oh, how do they encrypt a DVD so that you cannot play it, you cannot make a copy of it? The investigation itself, the act of investigating, is illegal. Okay, so that's a little bit different from the possession, making the possession of pirated material illegal, and also the action of actually making the pirated version illegal. It is the investigation itself that is illegal. Is that okay? In other words, what I'm about to do would be illegal unless I get the owner's permission and say, yes, go ahead and hack my program, I don't care. But since I wrote this program, I'm hereby giving myself permission to hack this program. So everything is good now. Huh? I hereby grant permission to Ouyang to hack the program hack1.stripped. We're all good now. OK, so now how do we hack this program? So when you're hacking a program, you're basically thinking the program was not written correctly. Okay? Because if the program was written correctly, there's no way you can hack it. So if you are trying to hack a program, you have to use an assumption of something is not written correctly in this program. So in this case, I'm relying on the assumption of, well, maybe the password, the length of the password can be too much, and then the program is going to crash. And when I give it a password that is too big, that's too much. Okay? So I can now run the program again, give it a really, really long password like that. Well, it still didn't crash. Okay? So what I need to do now is I have to create a systematic way to give it a long password. So now I say, okay, so this is my password. We'll use 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. That's exactly 16 characters. And then we'll go ahead and make copies of this. Okay. Oops. And if I want to make this really fast, I can say make 16 copies of this. And then I can make even more copies. Make, okay, yank all of this, and then make 4 more copies of these. Okay, so I'm making a long, really, really, really long password, okay, hoping that this is going to crash the program. Okay, so I'm going to run the program again, but this time I'm redirecting the input from the file. So I'm feeding the file that I just generated with a lot of characters into the program as if I'm typing it on the keyboard. Press the Enter key, segmentation fault. Good, I crashed the program. Okay, so any hacker that's doing any type of hacking, this is the first step. They got to crash the program first, because crashing the program means the program did not anticipate a certain thing. Okay, and the hacker will rely on that assumption to try to get into the program to control the program in the process. Is that okay? So now that I have crashed the program, what do you think is the next step? I mean, this doesn't tell me how the program died. I need to find out how the program died instead of just the fact that it died. So what is the tool that can help me to figure out how the program died? We have used that tool already in this class. GDB, okay, the GNU debugger. So we use GDB, and then we give it, the file, the executable, and inside I can run the program and still use the redirection. So this is how you can use redirection from inside GDB. This is going to be useful for your other classes. So if you're taking cisp 400, 430, you want to feed your program the same test file over and over again, this is how you can do it inside GDB. So you can have the same consistent test case, time after time, so that you don't have to retype everything from the beginning. Okay, so I run it, and once again, it gives me a segmentation fault, and blah 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 blah. Okay, it says it's attempting to execute at this location, or the execution of the instruction at this location is what is causing the problem. Okay, so now we have slightly more information. But what else do you think I need to know, when the program crashes? There are certain registers that are particularly important in the execution or the path of the execution of a program. Do you guys remember the program that I wrote on Tuesday, where main calls F, and then when F returns, we get to G, right? What got messed up? Something on the stack got messed up, right? And then when we tried to return, it returned to the wrong place. That's what went wrong, with that program. So that tells us which register is important. When your program crashes or do something that is not supposed to, what register should you be looking at? The stack pointer, okay? Now with the x86 architecture, especially in 64-bit mode, it is not register D that is the stack pointer. It has a stack pointer register. So what we'll do is we're going to look at all the registers and find out which one is the stack pointer. RSP is the stack pointer. Okay, this guy is our stack pointer. It's showing us an address. Okay, the address itself is kind of useful, but what is really important in this case is what is the content of that address. So what we want to do now is not only to know what is the stack pointer while the program crashed, but to find out what is on the stack when it crashed. Is that okay? All right. So now we use the X command here, X slash, I cannot remember how to display 64-bit again. Do you guys remember? Giant? Okay. So X slash GX, and then we use the $sign to refer to a special variable. RSP, a register, is known as a special variable, so we can refer to that. And we can also refer to, like, give me 8 giants, okay? Instead of 1, give me 8 of them. Okay, so it's showing me some stuff like this. You go like, well, we can definitely tell there's a pattern here, but is it important? Is it significant in any way? What do you think? What do you think is interesting about 66, 65, 64, 63, 62, 61, and then we got to 39, 38, blah, 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 blah. What is significant about those hexadecimal digits? They are ASCII codes. They correspond to ASCII codes. Okay? So what do you think is the character corresponding to hexadecimal 66? It's okay, you don't have to know because we have the ASCII table. So in Linux, you just go to the command line interface and you say man ASCII, and it will show you the ASCII table, which is really handy. So from here, we can see that in hexadecimal, 66 is corresponding to which letter? Okay, this is hexadecimal. 66 is corresponding to F. 65 is corresponding to E. So we got F, E, D, C, B, A. And then we got those 3, 9, 3, 8, and so on. So what character? Yes, go ahead.
What told you that those correspond to ASCII codes?
Because those are all less than 7F, and they're all greater than 20. So that is the range of printable ASCII characters. So when you have a bunch of bytes, and they're all between basically 20 and 7F, that's a pretty good indication that those are printable characters of some kind. What also gave it this away was the sequence. 66, 65, 64, 63, 62, 61, 60. It is definitely not random. And the only thing that is not random that we introduced into the system was the password. So that kind of gave me I doctored this whole thing, right? I came up with the whole thing. But if you were to look at this, this is a visual clue that it is ASCII. Okay? Okay, so we know that we are hitting the password. Okay? The password became the return address. That is why the program crashed. Is that okay? So based on what we learned on Tuesday, what do you think the program might have done to overwrite the stack to the point where the return address was clobbered by the password itself? Yep. It just kept copying the password from standard in into RAM, and it did not stop at the end of the array that is allocated to it. It kept going. Okay? Which function you can copy strings in C and C++? Come on. The name of that function is very intuitive. String copy. Okay? It's string copy. So now we can also look up string copy and ask the question, well, what is suspicious about string copy? String copy is this one, the first one. You specify the destination, is a pointer, and then you specify the source, and it will copy. It will keep copying until what? The terminator, right? The null terminator. So it will keep copying until it gets to the null terminator. But what if I have 600 bytes before I get to the null terminator, but the destination string really only has space for 256 characters. Would it stop at 256 with string copy? Nope, it keeps going. That is one very common reason why programs would crash, is we're trying to copy beyond the boundary of an array, and then it starts to chew into things that it really should not be overriding. And the return address is one of those things on the stack, and we just so happen to overwrite that portion. So are we doing okay so far with this program at this point? We good? Okay. But now we have a problem, because if you look at the password file that we created earlier, okay, so we look at password. This is a repeating pattern. I have no idea exactly where it stepped on to cause that problem to happen. So now how do I find out exactly where the point is? Do you guys see what I'm saying? Because we got a lot of 0 to 9, A to F pattern. I mean, it's an error on my part that to use a repeating pattern, so it's not easy to tell. But now that we have this pattern, how do we zero into the byte that is causing the problem? Yep.
Could you delete that, copy the text from the ASCII table, and then paste it in there?
We could do that. We could also do a binary search method, where we cut this in half and see if the problem is still there. If the problem is still there, we cut it in half again. Right? So we can basically just use the binary search method to try to zero into the 8 bytes that are actually causing the problem. So that's one way to do it. The other way to do it is to look at RAM in a different way. So we run the program again. So let me go back and use GDB to run the program. Run the program again, give it the same password file. It's going to crash exactly the same way. This time, I'm going to examine again. But the way I examine this time is to display 512 things. Each one is a byte. And this time, I want to interpret each thing as a character. So I'm no longer looking at ASCII, a hexadecimal representation. I'm actually looking at the character interpretation, the printable characters this time. Okay? So let's check out what this is going to do. Oh, okay, I didn't tell it where to start. So it's going to be $RSP, which is the stack pointer. So we can see that, okay, return for more, and we are still not running out. So that means the corruption part is 512 did not quite cut it. So I can delete 512 characters from the password file safely without making the program to go well again. It will still crash. Is that making any sense? Because I'm displaying what is from the stack pointer and up. These are all corruption, okay? It's corrupting at least 512 bytes more than it needs to. So I can remove 512 bytes from the password file, and the program will still crash. Is that okay? All right, so we'll do that. So we go back to the password program, go to the very end, 512 here, and there we go. 512 characters are now gone. And then we can run it again, okay? And it crashes at exactly the same place, which is fine. x/512 BC $RSP. Okay, it's still too much. So what we do is we keep trimming the password. So 512 back, delete this much, do it again. I mean, I'm pretty sure some of you can think of a faster way to do this, or write a script to do it, right? Do you guys think real hackers do it by hand, or do you think they do it by scripting? Whatever they can automate, they automate. All right, so we'll do the same thing. Examine 512. Oops, examine 512 bytes. Each one is a character. and starting at where the stack pointer is pointing to. This time we got something, okay? So apparently we get to this point and the corruption is ending here, okay? So this is the last one. So from the beginning, so now we can stop this. We can say Q to quit the printing, and then we can try to find out how many excess we're dealing with here. So we basically want to subtract this number from the stack pointer. All right, so, and this is a negative number, so I need to do it the opposite way, or we can use 2's complement too, which takes too much time. So we just flip the order of the subtraction. Argument to arithmetic operation is not a number or Boolean. Why would it say that? Well, doesn't matter. Regardless. If we look at this number here, can anyone tell me what is the value represented by this number? Okay, first of all, if I look at this as a signed integer, is it positive or is it negative? How do you know it's negative? All the f's, the most significant bit is a 1. Okay, that's how we can tell it's negative. How negative are we talking about? Is it really negative, or is it, it's pretty close to 0, just a little bit negative? Huh? It's close to 0. How do we know it's close to 0? What is -1? What does -1 look like as a 64-bit signed integer? It'll be all f's, right? This one is pretty close to all f's except for the last 2 digits, the least significant 2 digits, right? So we're only off by about 80, which is about 128 or so. So that means we are still in excess of about 128 characters in the password. So if I trim it back by about 128 characters, we should be getting close to the portion where it does matter. Is that okay? Are we doing okay so far with at least the idea of how we know how much to trim? Okay. All right. So we now go back and trim the file one last time. Go to the back. Go back 128 characters. Trim these. And this time, I am going to make these a little bit more unique. So instead of using the same pattern here, I'm going to use, all zeros for one and all ones for the second one. So this way, it is much more unique, and I can tell which one is causing the crash. So once again, go back here, run the program again. And it crashes again, which is okay. That's exactly what we want. And this time we can examine just a single giant in hexadecimal, where the stack pointer is pointing to. It's given us 313131, okay? So what would that be? Would that be the zeros, or would it be the ones? The ASCII code of 0 is 30 in hexadecimal. So these are the ones. Okay, so we know it's the ones that are responsible for this. The next question is, do we have any excess, right? Is it the last 8 bytes that is causing the problem, or is it the first 8 of the last 16 ones that is causing this problem? So we can now display 16. Each one is a byte and a character from where the stack pointer is pointing to. And we can tell that it is exactly the last 8 bytes that is causing the issue. Okay? Very good. Knowing this gives us hope that we can gain control over this program. Why? Because this is the content of the password file, isn't it? I have control over the content of the password file. It's a file that I created. Is that right? So if I can control these bytes in the file, and these bytes are being used as a return address, don't you think I now have control over where it is going to return to? Okay, so the next question, now that we have gained control over the steering wheel, The next question is, how do you want to steer it? Is that okay? So we want the program not to give us that message of read the fine Digital Millennium Copyright Act, right? So the next thing we need to do is to find out how does it print that message? Because if I know where in the program it prints that message, it might give me some clue of how I can bypass that problem, how we can bypass the password checking mechanism. Is that making any sense? Okay. So now we need to rely on another tool called object dump, okay, obj dump. And if you do a man page on obj dump, D-U-M-P, it gives you a lot of options, including disassembling and stuff like that. This is one program that is really helpful. The other one is called hexdump, H-E-X-D-U-M-P. So let's use hexdump first. So we use hexdump dash, I think, uppercase C on the executable, which is hack1.stripped. There we go. And then we'll pipe it through less so that we can actually go through something like this. So hexdump is a very simple program. All it does is to go through every single byte of whatever file you give it, and it will tell you what is the character corresponding to that particular byte. Okay? It will try to look at each byte as an ASCII code and tell you what printable character is corresponding to that. So what I'll be looking for is DMCA or something like that. Aha, found it, okay? So it is at an offset of 670 in the executable. So it's giving us some additional clue of where I need to look later on. So I'm going to use the whiteboard here to write down 6, 7 is not exactly 0. It is 0. Okay, so it's at the very beginning. So this is where we can find RTFDMCA. Okay? This is good. But now we need to look into the actual code of the program and ask the question, where in this program am I passing the address of blah, blah, blah 670 to a subroutine that can actually print something? Okay? That would be the job of object dump. So we know we have to look at the man page of object dump, and disassemble all seems to make sense, dash uppercase D. So we take a look at that, obj dump dash uppercase D, and then you give it the file that you wanted to disassemble. And by the way, as long as you have an executable, you can do this. There's no symbol table or remaining in this particular program. So I have lost track of all the symbols in the original program already. But that doesn't stop me from doing this and doing a less. And you can start to see these are assembly code for another architecture. It's for the x86 architecture. And we want to look for 670 and see whether that is found here. So we got that. And this is actually jackpot. Because if you look at the first line, it says move, right? So what do you think move does? Okay, first of all, can you actually move bytes around in memory? Can you physically take some transistors from one physical location and transplant those transistors into a different location on the die? No. So move does not make sense. Okay? Move is what we call what do you call words where the meaning is not fitting? Misnomer, very good. So move is a misnomer. It is copy. Okay? All it does is copy. Okay? What it is doing is it's copying EDI. It's actually the other way direct. The other way is copying the constant 400670 into the register EDI. And what is the next line saying? Call Q, okay, and then some location. What is put S? Do you think put S has any significance? So let's say you don't know what is put S. What do you do next? Based on what we have done so far, yes? It's put string, exactly. But what if you don't know what it is, okay? But the fact that it is displayed in symbolic form means it is probably a C library subroutine. If it is a C library subroutine, the man page probably has an entry to describe it. So the next thing we do is we look up the man page and say, tell me what is put as. And right here it says, put as, okay, scroll down a little bit. Put as is what writes the string and the trailing new line to standard out. Ooh, does that make sense now? So we have located exactly where in the program that it prints RTF DMCA. Yes?
So you knew that it was a ASCII function because it was in the brackets?
In the brackets?
What made you say that it was probably, what made you think that it was probably ASCII?
Well, okay, I located this because of the earlier hex dump. So it's at an offset of 670. The entire program is offset by 400000 from the actual location 0. But put as is a special label because this assembler is telling you and go like, oh, we know what this location is. It is the entry point of the subroutine put as.
Okay, so it's a label. The labels are just in the brackets?
Yes.
Okay.
If it knows a particular C subroutine is corresponding to that location, it would try to give you a symbolic name so your program is easier to read. So in this case, we know this has to be corresponding to the branch where the password did not match, right? So if a program has a branch to deal with the case when the password did not match, it must have a branch to correspond to the case when the password does match. So now we have to analyze the surrounding instructions and try to figure out, okay, do we recognize a conditional statement here? That is the question, okay? I know we are running out of time. So we'll use the next 5 minutes, okay, and then if we run out of time, I can continue next time. What do you think is JE? Jump if equal, okay, which is the same thing as a JZI for us. It's called a JE in this particular architecture. So it's trying to match, okay, the key point is it's a conditional branch, okay? Sometimes it branches to location 5BA, which is here, which is exactly where it prints the error message. If it does not perform that, it will, no, yeah. So the other case is, the else case is here. Or the then branch is here, the else case is here. So the question is, how do I force the program to go to the then branch instead of the else branch? It is currently going to the else branch, which is here. It's trying to get to location 4005BA, but since I overwrote the return location or the return address, it branched to the wrong place and crashed the program, right? So now that I have control over the steering wheel, where should I steer it to? I should steer it to the other location, right? The other branch, which is location, okay, I need to line up everything here. Location 4005AE. So let me write that down. I probably won't have enough time to completely finish this program, but I can at least talk about the concept. So 4005AE is also important because all that is remaining for me to do is to change the first 1, 2, 3 bytes of those 8 ones that is corresponding, that is causing the program to crash, to exactly AE in hexadecimal, 05 in hexadecimal, and 40 in hexadecimal. Then the program is going to crash, quote unquote, but it's going to crash directly into the branch that corresponds to when the program thought that I entered the password correctly. We can check the address. Yes, so we can actually doctor the stack content and then continue execution, and then we'll see the program that it's going to say, "Yep, welcome back. You're fully authenticated now." So I just ran out of time, like by a few minutes, of not being able to complete the entire thing, but you can actually kind of tell that what you're learning in this class is what is enabling you to understand, at least in concept, how to hack a program. Yes, question? Oh, okay. All right, so we got 3 minutes before 7 o'clock, so I'm going to ask you a few questions that are not technical. For question number 1, why do you think this might be helpful? Or do you think tech is just going off the tangent again and talk about something that is totally irrelevant to anything that you might do in the future? Yep.
You can understand how someone might take advantage of the program and stop them from doing that.
Yes, that's one. Go ahead.
More or less same thing. It lets you design your program in line of faults like this.
Uh-huh. And you can also be a white hat. In other words, you can be working for an antivirus company, okay, and gaining an understanding of how virus and worms and other exploits work can help you figure out a way to detect programs getting exploited. Okay, so that's one. You can join the one of the government branches, because do you think governments try to hack into each other's computer? It would be dumb not to do it, right? So do you think this country has teams of people to try to hack into computers of other countries? Yes. So, I mean, do you think those jobs are well-paying? Why do you think those jobs are well-paying instead of like a game programmer? Huh? Exactly. You got to keep them well paid so that they won't be lured by money from another government, right? And yes, so what you said earlier was true as well. If you know how a program can be hacked, then you can try to write a program that does not have these flaws. Because in this particular case, the flaw was string copy. So if I use string and copy, I would have made this program safe already, because the copying would have stopped by the size of the array and not by locating the null terminator. Okay? So that's kind of the, what I want you to get out of this class is really just getting a general sense of how programs get exploited. I'm not going to quiz you guys on, okay, here's the program, try to crash it, okay? Or this is the grading program. If you guys can, by default, it will give everybody an F. If you can crash, if you can hack this program to give yourself a different grade, that would be actually your grade. That would be brutal for a class like this, right? Huh? For the final exam? Let's make the final exam worth 100 points so you guys can redeem yourselves, right? All right, so there's no new lab for today. We'll just be continuing to work on the Fibonacci program. If you're all done, you can go home. Huh?
Will the lab be open today?